Hello, everyone. See, just got another email from President's office that another member of the OCC community has tested positive. They were last on campus June 26th, so they don't tell us anything more than that. And as I'm sure you heard, well, Newsom is shutting everything down again, so we're back to that shit. Anyway, so let's get started on today's stuff. So there we go. All right. So we want a new one. And we're at 185. And today we are going to be looking at curvature, and then we're going to do some polar coordinates. Coordinate. All right. So we'll go to this, the draw, black. Okay.
Professor, has everyone got their grades for the exam?
Hold on. For the, there might be a couple that I couldn't open up. I'll check in a little bit when I get out of this.
Okay.
Why, are you missing yours?
Yes, I haven't got it, and I emailed you through Canvas. Maybe that's why.
Okay, I haven't got that. I haven't got it yet. I generally look at emails in my normal place. The Canvas one, I find that I just need to look at them at one place.
Oh, okay. If you want, I can send it to you there in your normal email.
Just send it. Well, you should be able to submit it through Canvas. There was one exam that I couldn't read. That might be it.
No, it's definitely not mine. That's okay. For sure. Yeah.
Yeah, there was one that was too light, and I think I even submitted a comment on it.
No, I couldn't submit it through Canvas because it was giving me an error, so I emailed it.
Oh, okay. I'll look. I'll dig around. What's your last name?
Diana Nejad.
Okay. Curvature. Okay, so imagine that you were trying to ride your skateboard around this little loop here. So imagine you're going on that. Now let's say the distance here, is from here to here. Okay. As opposed to you get on another one and you go like that. Okay, so you're traveling here, you're traveling here. Now, the distance is still going to be the same, okay? But hopefully you guys all have some kind of experience with this, like on a skateboard or in a car, riding a big wheel, that it's going to be harder to go on this turn than it is to go on this turn, right? Okay, so the reason for this is because this curve right here, at least down here, looks a lot more aggressively turning than this one here. Okay. And so what we want to do is we want to attach to a curve a number called curvature. Okay. So the way that we're gonna set this up is as follows. So this is kind of a scaled down version of what Gauss did. But he did this three-dimensionally. Okay, so we're gonna have this curve like this. Here's like the XY grid. And some curve that's gonna be going like this, let's say. Okay. Now at this point, let's say P right here, we've got a tangent line that we can draw. Why did I do that? Okay. So for the point being right there, we'll draw this tangent line, which I'll draw in red. Okay. So this is the tangent line of the curve. And this is just our curve C. Okay. Okay, now down here, there's an angle that we can measure, this angle phi. Okay, now as this point slides around, like let's say it gets to be over here, then the tangent line, which is actually going to cut through the curve again here, is now going to be this much. Okay, so that would be that angle that we're measuring. Okay. Okay, so if we were on a straight line, we would want to define, if we had a straight line, we would, whatever we come up with curvature, we want the curvature of a straight line to be 0. Agreed? Okay, because a line isn't going to curve. So if this is my curve, which is just a straight line like this, going like something like that, no matter where you are on the curve, the tangent line is the line itself. And so for C being a line, this phi is constant. Okay. Now, if we have something like this, let's say, where it's kind of sharply turning, let's say that we are traveling on the curve this direction. Okay. So we will go from this point, let's say, to this point here. The tangent lines are these two guys. Okay. And like, let's say I'm starting from here at point P1 and I'm going to move to point P2. Okay, well, then this is going to have this angle, which is phi1 versus this angle here, which is going to be phi sub 2. And as you can see that by just traveling relative to the screen a short distance, this angle, this phi thing really changes, okay? Now, if I draw a similar situation here and blow the picture up, okay, so if I was to, whoops, let me get back into black. Okay, so if I was to do something like this, okay, now, and draw a similar curve, but much bigger, okay? And let's say I was going to go from the point P1 to the point P2, okay? So we're still going to have a switch. But if we want to talk about, where's that guy? Nah, shit. We want to talk about what's the relative parameter here, okay? Let's say that this has an arc length of S, okay? If I, on this smaller curve, by traveling a distance of S, I get from P1 to P2. Now, if I start at this point, let's call it P1, which is I'm kind of at a similar place. If I move to the point P2, which is going to be like there, I've done the same amount of arc length, S, and the two tangent lines haven't, well, that was a terrible attempt. The two tangent lines, the angle phi is going to change, but it's not going to change as drastically. Okay, so this is why we were talking about arc length, okay? So some assumptions here. Our curve C is going to be given parametrically by x equals x of t, y equaling y of t, where the t is going to run between A and B, okay? So, number one, we assume that C is smooth. Okay, now smooth means what you think it means. It means it doesn't have any jagged places. There's no place in the curve where it does this, has a cusp, and there's no sharp, like, absolute value thing. These things are out, okay? Now, the word smooth, we can do better with that, but right now we're just going to assume that's what it means to be smooth, okay? And we'll talk when we get there later about a better definition of that. Now, from this, since we assume the curve is smooth, then the angle theta, the angle phi above this is a function of x and y. There's a couple places in the 185 class where we throw in how do you do a function of more than one variable. But clearly back up here in these pictures, that as this point right here is moving along, because the curve is smooth, this angle is going to depend on wherever you are on the curve, okay? And number two, we assume that this phi of xy is differentiable. Okay. Now I'm going to put that in quotation marks. Okay. Because what does it mean for a function of more than one variable to be differentiable? And it is a startling letdown when we get up to Math 280. The definition of being differentiable is not as slick as it is for us with these one variable things. Two variables, it's a big mouthful. And I can show you where it is in the book sometime, and you can go get disgusted with it on your own. Okay, but anyways, we're going to assume this is somehow differentiable. Okay. Okay, so now back up here at this curve. I'm kind of looking at this one right here. This guy. Okay. What Gauss realized was that and I'm just kind of simplifying his discussion in 3 dimensions to 2 dimensions. What Gauss realized was that this number, which we're going to call curvature, should have something to do relative to the arc length. Because if you travel a distance of s on this curve, the angle is going to change rapidly. Now, if you started at the kind of the similar point on the second curve, shit, all that stuff got erased. Well, you get the idea, okay? So what we're going to do is we're going to define curvature. So definition. Given a curve C, which is given by x of t, y equaling y of t, where t is going from A to B, is smooth. Okay, then with this angle defined above, what we will do is we will define the curvature, and this is the Greek letter kappa, okay, to be the magnitude of the derivative of this guy with respect not to t or x or y, or it's due to that. So it is how much this is changing with respect to arc length. Okay, so 2 curves. One curve goes like this, and one curve goes like this. Okay, when you start here and go 1 unit in arc length, you might be here. Whereas if you start here and go 1 unit in arc length, you're going to be right there. Now, wherever this x-axis is, this angle is changing rapidly, okay? It's going from this to this in 1 unit of arc length versus this guy. This is me writing cycling. That was terrible. Well, you get the idea, okay? The angle is not changing all that drastically, okay? Okay, well, somehow we're going to have to figure out what this formula is. Okay, so our problem here is going to be to find this curvature kappa by using the curve at hand, x of t and y of t. Okay. Okay, so let's start off with this. I'm going to draw the picture one more time here. So here's our guy coming in like this, okay? And here's our point, P. And here's our tangent line, like so. And here is our angle, which is going to be this guy there. And this is the x and the y axis. Okay. So if I was to draw a triangle over here like this with phi in there like that, okay, then wouldn't like the tangent of phi be given by this y coordinate over this, x distance from there to there, like so? How about like this? Instead of using those, let's use the words from our childhood. The rise or the run. So the tangent of the phi is rise over run. Okay? But rise over run, that's equal to slope, right? And slope is dy dx evaluated at that point P, because that's what the slope of the tangent line is. Okay? So that means that the tangent of this phi is equal to whatever the slope of this tangent line is. So that means we have figured out a way to express phi, at least, in terms of the x's and the y's. So it's going to be the tan inverse of dy dx. Okay, now the formula or the definition was that the curvature was going to be the derivative, the magnitude of the derivative with respect to arc length. Okay. So what we can do here is we can say that this phi, which is the tan inverse of dy dx, okay, then that's supposed to be inverse. This is the tan inverse of y dot divided by x dot, okay? Recall that was something that we had, that dy dx turned out to be this nice formula divided by dx dt. Okay? Okay, now, at this point, this is a function of t. Would we agree with that?
Yes.
Okay. All right, so if I was to take the derivative of this guy with respect to t, it's going to be the derivative of tan inverse, which is 1 over 1 plus the argument squared times the derivative with respect to t of this y dot over x dot. That's the chain rule step. Okay, so it's 1 over 1 plus y dot over x dot squared times the derivative of the top, double dot, times the bottom, minus the derivative of the bottom, x double dot, times the top, all over the bottom, x dot, squared. Okay? So if I distribute this through, what I get is y double dot x dot minus x double dot y dot divided by x dot squared plus y dot squared. Okay, and again, you know, the y dot is the derivative with respect to t. Okay, now remember what we need. We have, this is d phi dt. What we need is d phi ds. Okay. So maybe we can do some chain rule stuff here. Okay. Let's see. Start playing around with the chain rule. D phi dt is equal to d phi ds times ds dt. And once again, this is why the Leibniz notation has survived. Okay. This is like, you know, even more evidence that, you know, he knew all of these results and he was just backing into them. So his fraction canceling stuff looks like it's actually working. So from here, what we see is that the d phi ds piece that we get is going to be this d phi dt divided by ds dt. Okay. Okay, now for parametric, the s, whoops, the s of t parametric form is going to be the integral from a up to t of the square root of dx dt squared plus dy dt squared dt. So by using the fundamental theorem of calculus, ds dt turns out to be just the square root of x dot squared plus y dot squared. Okay. So when we plug that into this formula right here, we find that d phi ds is the d phi dt guy, which is this y double dot x dot minus x double dot y dot over x dot squared plus y dot squared. And now we need to multiply this by 1 over ds dt. So that's 1 over the square root of x, let me say x, x dot squared plus y dot squared. Okay, to finally arrive at the following formula, that the curvature k, which is this magnitude of d phi ds, is going to be the magnitude of y double dot x dot minus x double dot y dot divided by x dot squared y dot squared to the 3/2 power. And that's our formula that we get for curvature. What do you think about them apples, huh? Any questions on that?
Crazy.
Yep. So it's a little more involved, 3 dimensions, obviously, but it's the same kind of principle. Okay. So let's see if it's going to be doing what we hope it's doing. Okay. So like, for example, if we let x equal t and y equaling mt plus b, this is the line y equals mx plus b, right? Okay, now x double dot is 0. Y double dot is 0, right? So the numerator, the curvature, would be the magnitude of 0 over the derivative of this thing squared plus this m squared raised to the 3/2 power. Now all we care about is that doesn't equal 0. So, whoops. So this equals 0. Okay, so at least we get that out of it. Okay. Now what about a circle? Let's say we had x equaling r cosine t, y equaling r sine t. Now, I'm sure everyone here at once in your life has been on some kind of a merry-go-round, either at Knott's Berry Farm or the fair or Disneyland. Okay, so if you're going around a circle, and let's all pretend that's a perfect circle, does it feel any different going a distance of 1 unit of arc length from there to there than perhaps going 1 distance of arc length from there to there? It's like the curviness hasn't changed, right? Okay, so the curvature of a circle should be a constant number, all right? So let's see what old Gauss came up with here. So with our curvature formula, we've got x dot is negative r sine t. X double dot is going to be negative r cosine of t. The y dot is r sine t. And the y double dot, oops, that's supposed to be cosine. The y dot is r cosine t, and the double dot is negative r sine t. Okay, now I'm going to plug it in the formula. Formula is, where is the formula? Up there? There, let me stop it. This pen is so fidgety. Okay, so I've got y double dot x dot minus x double dot y dot divided by this x dot squared y dot squared to the 3/2. Okay, so let's do this mess. Okay, so x dot times y double dot. So that's going to be r squared sine squared of t minus x double dot negative r cosine t times the y dot, which is another r cosine t, then divided by this thing, x dot squared. So that's r squared sine squared t plus the y dot squared, which is going to be r squared cosine squared of t. Simplify this a little bit. This is going to be r squared. That's supposed to be 3/2 power. R squared times sine squared t cosine squared t divided by, now this r I'll factor out to the 3/2 power, r cubed, and then it's going to be sine squared t cosine squared t 3/2 power. And of course, these are ones, and so you get r squared over r cubed, which is 1 over r. So the curvature that we get, which is the magnitude of all of that mumbo jumbo, ends up being 1 over r. Okay, so as the radius increases, the curvature decreases. Okay, so let's say that you were, so if you were walking at Cape Canaveral on the runway that the space shuttles used to land on, that runway was built not as a flat surface, but it actually follows the curvature of the Earth. Okay. Now, this is about the only place that I know of where you can actually walk, and if the Earth was a perfect sphere, you would be walking, you know, on this curve. Okay, now, when you're there, you don't perceive that you have gone down, you know, or around or whatever. You look at this as just like a straight line, okay? So the curvature should get smaller as the circle gets bigger, okay? And notice that what happens in the limit as r goes to 0 through positive values of the curvature, this thing goes off to positive infinity because it would shrink just down to a little point right there. Okay. All right. So let's see here. If, new topic, curvature still. If C is given to us as y is a function of x, okay, then we can parameterize by letting x equals t, and then y is going to be this f of t, okay, then x dot is 1, x double dot is 0, y dot equals f prime of t, and y double dot equals f double prime of t, okay? So in the curvature formula, what would happen is we would get the y double dot x dot, okay, so that's going to be f double prime of t, okay, and then divided by, and then minus 0, okay, because it's x double dot, which is, that's the 0 thing, okay, and then the x dot squared, which is 1, plus the y dots squared, which is the f prime of t thing squared. And if we like, we could write it as the magnitude of f double prime of x. And then, whoops, this has to be, forgot my 3/2 power, divided by the 1 plus the f prime of x squared, all raised to the 3/2 power. Okay. And that's how that one goes. And sometimes it gets written with Leibniz notation and so on. Okay, now he doesn't really have any exercises for these, but eventually, you know, we're gonna throw them in here. But I'll just set up one and we'll see how far we can get with it, okay? So let's start with a easy guy like y equals x squared. So our f of x is going to be x squared. Okay. So that means that what am I talking about? Well, of course we'll be able to finish this. F prime of x is equal to 2x, and f double prime of x is equal to 2. So the curvature is going to be 2 divided by 1 plus 4x squared to the 3/2 power. And we don't have to worry about that being negative, do we? The curvature cannot be negative. Well, that's not true. We can define some kind of negative curvature, but it's going to be in some weird journal, and maybe like, you know, Einstein stuff. When we get to 285, we'll be talking about norms and inner products and, you know, other things, and where certain conditions can be relaxed. But anyways, so this is the curvature of the guy that we want. Okay. All right, now let's see what happens here. When we get close to 0, shouldn't the curvature at 0, 0 be the maximum? Okay, so at the point 0, 0, the curvature is going to be 2. Okay, now what happens as we move away from the origin, like we get to this point or this point? Well, notice because of the x squared, whatever the curvature is here is going to be the same as the curvature of this guy right here. Okay, and the limit as x goes off to infinity of the curvature is going to be 0, which means that without at infinity, we won't be able to distinguish this from a straight line. Okay. So let's look at another guy, like, for example, the ellipse. And y equaling b sine t. This is the ellipse. Okay. So we're going to find the curvature as a function of t. Okay. All right. So the a's and the b's here are going to be interesting. Okay. So let's see. X dot is going to be negative a sine of t, and x double dot is going to be negative a cosine of t. Y dot is going to be b cosine of t, and y double dot is going to be negative b sine of t. Okay, so our curvature as a function of t is going to be the magnitude of, and it's y double dot x dot, so that's going to be ab sine squared of t, and then minus x double dot y dot, so that's going to be plus ab times the cosine squared of t divided by a squared sine t, sine squared t, plus b squared cosine squared t to the 3/2 power. And again, now we can drop the absolute value. We recognize that the numerator is just going to be a times b, but the denominator, unfortunately, can't do anything with unless, why does it always go straight back to that stupid thing? A squared sine squared t plus b squared cosine squared t to the 3/2 power. Okay. Okay, now on an ellipse, let's say this is where A is and this is where B is. This ellipse come around like that. I think we would expect it to be the most curvy. Fuck. Wish I could just lock it into the pencil. So there's A, there's B. And now I draw a shitty one.
Bobby.
Yeah.
So if you erase something by at the top under the time and the date, there is like an arrow. You can like just click it and like undo the thing.
There's an arrow.
Yeah, no, yeah, at the left corner at the top.
The left corner of the screen.
Yeah.
That arrow.
No, the one
Next to the search button,
Yeah.
next to the
Below date
magnifying
and
glass.
time. Below date and time.
Mode.
You know where the search thing is on the left corner?
The search thing.
They're talking about where the time
The
is in the
magnifying
top
glass,
corner.
top left.
Yeah, the magnifying glass. Next to the magnifying glass, there's a,
A little arrow.
yeah, that one.
I don't think that. What does that do?
That
That says
basically
undo.
backtracks.
Are you guys talking about the undo thing on the top left?
Yeah,
That's the undo symbol, Bobby. You're
No,
using
I'm trying to
iPad.
lock. I'm trying to lock it so the pen will only go to eraser when I tell it to, because it just randomly switches to eraser.
That could be a feature, like part of your pencil with the iPad. Like I'd look into that. That might be like if you tap it twice, something like AirPods, how they work.
Yeah.
Might want to look.
By the
into
way,
it.
don't anybody buy the new AirPods. They suck. They
Oh, the
fall out of your
$250
ears.
ones, you mean? The AirPods
Yeah.
Pros?
They fall out of your ears, and they're just.
Well, no need to have them anymore, man. Gyms are closed again, so
Yeah. Good thing I got a gym in my backyard.
there you go, man.
Can't believe this shit. All right, well, where would we expect this to be the most curvy? Probably at these spots, right? Okay. Now, this is going to be a calculus problem from hell, but I do want to see if we can investigate this. Now, again, our t is going between 0 and 2 pi. Okay. So this will be a little refresher in our Calc 1 skills. Our curvature as a function of t is this number AB times a squared sine squared t plus b squared cosine squared t to the negative 3/2 power. So there's a trick that we can, well, not really. Okay, let's just suck it up and do it. All right, so here we go. I'm going to find the derivative. And again, I went into eraser. K prime of t. So this is going to be negative 3/2 of AB times this a squared sine squared t plus b squared cosine squared t to the negative 5/2 power times the derivative of the inside. And the derivative of the inside is 2a squared sine, let's start over. Okay, it's going to be 2a squared sine of t times the cosine of t. And then this is going to be minus 2b squared cosine t sine t on the inside like that. Okay, so it's equal to, in the numerator, negative 3ab times 2a squared sine t cosine t minus 2b squared sine of t cosine of t. And then down here, we're going to have 2a squared sine squared t plus b squared cosine squared t to the 5/2 power. And this is going to be, I mean, I don't know where you want to go with this. I can go to, that's the, each one of these is the sine of 2t. So it'd be a squared minus b squared times the sine of 2t. Okay, so first of all, the denominator is never going to vanish. Do we all see that? Because everything in there is positive, and sine and cosine are never simultaneously negative. Okay, so if the derivative is going to be 0 and we're going to have a max or a min, so if kappa prime of t is to equal 0, that's going to mean that 2a squared minus 2b squared sine t cosine t equals 0. Well, since a and b aren't the same, that's not 0. So that's going to mean the product of the sine of t times the cosine of t is equal to 0. Now, instead of solving a hard trig equation, let's just go through where sine and cosine are 0. Okay, so you see how that's worked out? This is t equals 0. And then this is with a t equals pi over 2. Okay, so it is giving us. Now, of course, we would have to do some kind of second derivative test or, you know, something like that. Okay. All right, so anyways, we will be looking more into curvature when we get to calculus of multivariable calculus. All right. Okay, so on your little assignment that I'll put out tomorrow, there'll probably be a curvature problem or two. Okay. All right, let's talk about polar coordinates. Okay, so section 10.3, at least in my book I'm using, is polar coordinates. And give me 1 second, I gotta go blow my nose. Allergies are acting up. I'll be back in like a couple minutes.
So how was the first 10 minutes of class? Has it just been this the whole time?
Pretty much.
Rough.
I mean, a hard time. Like,
I think tomorrow, Nathan. I think the next test is tomorrow.
Yeah, tomorrow.
oh,
It's not really a test. It's more of an assignment. Now my daughter's freaking out. This is what it's like living with a 13-year-old girl. Okay, so any of you that missed it back in pre-calc, and that includes me, I never did polar coordinates in pre-calc. Then again, my class wasn't called pre-calculus, it was called math analysis. Okay, so one way to represent this point P would be by specifying where the X and the Y came from. Now, this idea that we take for granted of just, set up an X and a Y axis and this and that, this was revolutionary at the time. And again, done independently by Pierre de Fermat and what's his name? Pardon. Okay, well, another way to represent this is if I could measure how far it is away my point is from the origin, and then maybe measure what this angle is. Okay, then I could also represent this guy by reporting the 2 points like this. Okay. All right, now there are some problems that are going to arise. Okay. First of all, the origin. Hold on a second. All right, so now is this how you spell origin?
You're missing
Or-
an I. It's
or-
O-R-
Origin.
O-R-I-G-I-N. Second time is correct. Yeah.
You think so? Anybody vote for this one?
No, I know that's correct. No, it's not organ. It's origin. O-R-I-G-I-N. 100%.
Okay, next semester I'll have another class and they're going to insist it's that one.
Are you serious?
Oh yeah, we go back and forth on it,
No way. There is not somebody who thinks that organ is origin.
Sure.
I mean, that would technically origin, but it wouldn't, because the I after the G makes it sound like a J. No, man. Yeah. I taught English for a while. No, that's crazy, but sad.
The origin. Let's see how old Stewart spells it. Maybe I can find the word origin. Well, eventually. Okay. So we have a problem representing the origin, okay? Because if our point P in XY is the point 0, 0, and this is in XY stuff, if the point R theta is going to have a 0 in the R, the theta could be anything we want, right? Because you haven't gone anywhere, okay? So this is the first issue that we run into, okay? So, one. The origin, okay, O, which is occurring at the point X equals 0, Y equals 0, doesn't have unique representation. Now, when you say you taught English, is that like you taught English for real, or you taught English to Chinese students in mainland China online?
Oh, I mean, not online. I was living in China, but yeah, I taught it to like high schoolers and mostly elementary.
You were Robin Williams in Good Morning Vietnam.
If that's what he did, man, I've never seen that movie. I do know it.
I would like to buy some cheese and some butter.
Yeah,
Oh, you got to watch that movie just for that scene.
Shenzhen, and I also lived in Hangzhou. If you've been to China, it's pretty cool. But yeah, anyways, the J sound from the G when it was followed by an E or an I is a common thing.
Mhm.
Yeah, I just haven't seen origin ever spelled the other way that you said.
Okay, so what we need to do is we're going to make an identification. Identify that anytime you have an R theta and you have a 0 in the R and a theta here, we are going to identify that all of those points as equivalent to this point. Okay. Now, there's another thing that comes up here in a second, but for right now, when we start graphing things, and we'll be graphing one curve and another curve, and it'll look like the graphs intersect 9 times, yet when we do the math, we can only find 4 places. So a lot of this has to do with this non-unique representation of the origin, okay? Okay, so we are sometimes going to have polar functions. Okay, now these are slightly different from our y equals f of x stuff. If you are, real nerdy, you know that the x coordinate is what is called the independent variable, and the y coordinate is called the dependent variable. And when we report x and y, we report the x first, and then the independent variable, and then the dependent variable. And that's just the convention that we've adopted. Okay. Now, it may very well be that there's some societies that we have lost track of. Stuff's getting discovered all the time. And like that Göbekli Tepe, which was, predates the pyramids by about 10,000 years. Who knows? Maybe they invented some stuff like this. We do know the Babylonians invented some kind of trigonometry. You can get on YouTube, and this stuff is fascinating. Okay. Anyways, with us, because the theta is the restriction here, it's only going to go between 0 and 2 pi, right? Okay. So since theta has the most restrictions on it, it's going to go from 0 to 2 pi like that. Instead of writing theta as a function of r, we are going to have r as a function of theta. Okay, so for example, we might have r equals the sine of theta, or we might have r equals the cosine of theta over 2, or something like that. Okay, now the point that I'm trying to make here is that r will sometimes be negative. Okay, now this is not something that was in the game plan, right? Because the r is a distance you are away from the origin. Okay. And so the r needs to be bigger than or equal to 0. Okay. But if I was to, like, for the r equals the cosine of theta over 2, for r equaling the cosine of theta over 2. So, like, what if I plugged in, let's say, theta equals 3 pi? Why the hell not, right? Okay. So that means the r would be the cosine of 3 pi over 2. And that's going to equal, come on, eraser, 0. However, let's say that we use theta equaling let's say let's see, what do I want here? Well, it'd be easier for me to do it with the sine function because it's the same phenomenon. Okay. So for the r equaling the sine guy, okay, if we let theta be 3 pi over 2, the r is -1. Okay. So let's say that we were given some negative r comma theta, where r is a positive number. So if I surveyed each of you independently and said, okay, if this is the point P that is the guy r theta, where would you put this point Q? Where would you put it? I'm asking.
Above.
Are you thinking,
Second
okay,
quadrant.
so when you see, are you thinking opposite when you see this negative right there?
Yes.
Yeah. So if we draw the line that extends this line segment like that, and if this is a distance r, see, I didn't do that, fucker. Okay. So if this is r right there, and you know this is the angle theta right there, then this point right there will still have its r, but this angle is now going to be theta plus pi. Okay. And so this is going to be yet another one of these identifications. Okay. So if the thing in the R slot is negative, okay, so let's again assume I have R being a positive number, okay, like this, okay, where R is going to be positive. So what we're going to do is we're going to identify this point, negative R and theta, with this point, R theta plus pi. Okay. Now you notice that I don't say equal. I have this arrow for identification. I have a real hard time saying things are equal when they're not. And mathematically, you know, so this is just an identification that we make. Okay. So if we were asked to plot the point, let's say -2, and let's say -2 and 11 pi over 6, Okay. Well, what we would do is we would say, okay, this is going to be equivalent to 2, and then 11 pi over 6 plus pi. Okay. So it's going to be 11 pi over 6 plus 6 pi over 6. Okay, now what I'm trying to do here is whittle that angle down. Okay, so that's 2, and then that's 17. So how many 4s are in 17? 4. So this is going to be 4 pi wait, what am I trying to do here?
Plus pi over 6. Are you trying to do?
Well, what I'm
17?
trying, I'm trying to simplify this angle. 17 pi over.
Yeah, wouldn't that be over 6? So that would be 2 pi plus 5 pi over 6.
5 pi over 6, 2, and
2
then
plus
5 pi over 6. Okay.
Yeah, it's not 2 pi plus 5 pi over 6.
Well, it's this angle plus pi.
Oh,
So that's 17 pi over 6. And if I take the 12 out of there, 12 over 6 is 2. So that leaves me with 5 pi over 6.
okay.
Okay, so this guy gets plotted back over here. Okay. Now, there's homework exercises for you to plot these points, and I don't know if you're going to actually do them or not. I doubt it. Okay. So, conversion equations. Did I spell conversions? Obviously not, because I forgot an R. Conversion equations. Okay, so we have a point reported to us as X and Y, and maybe we want to switch over to R and theta or vice versa. Okay, so we just draw a picture up here and we'll start writing some stuff down. So this is your X and Y axis. Here's our point P, and it has coordinates X, Y. So that means it's a Y from there to there and an X from there to there. And this is R, and that's theta. Okay, so one equation that we see is that X squared plus Y squared equals R squared. So that means R is the positive square root of X squared plus Y squared. So if you're given the X and Y, you can determine the R. Okay, now as far as the theta goes, this is where we have a kind of an issue. If I start with X and Y, I want to get like R and theta. Well, I know that the tangent of this theta is equal to Y over X. So that would mean that the theta would be the tan inverse of Y over X. Okay, now the reason I put a star there is because there is ambiguity. Okay, so let's draw 2 points. Okay, this point here is going to be the point -1 and 1. This point down here is the point 1, -1. Now, when I draw this line, and just so happens I draw this line too, okay, that there are 2 angles here. That's one angle, theta 1. And then there's this angle that goes all the way to there, and that's theta 2. Okay, so let's say I called this the point P and this the point Q. Okay, so for P, well, the R is easy enough, square root of 2. And the same for Q as well, right? Okay, but the theta is the tan inverse of 1 over negative 1. Versus with Q, the theta, the R is still radical 2, but the theta is the tan inverse of negative 1 over 1. Okay, now, your calculators are not going to make a distinction between these two things. Your calculator is going to recognize just the number. And it's going to give you that as your answer, which we pass along to 7 pi over 4, right? And the 7 pi over 4 angle, that looks like that theta 2 guy. Okay, so if you were trying to get the point P represented, you have failed because what you've gotten is the point Q. Okay, so as I keep telling you guys, the reason that the defense budget is so large, it's because of bad math. Can you imagine how many hours of wasted computer time where somebody years ago coded this stuff in and everything was crashing? We use polar and later spherical coordinates all of the time. Anytime you have some kind of circular or spherical symmetry. So like, for example, in physics, gravity is spherically symmetric. The Coulomb force is spherically symmetric, as far as we know. Okay, at least in the model it is. Magnetic force, a lot of spherically symmetric stuff. So in Math 280 next semester, you'll take the next logical step and turn this into three-dimensional spherical coordinates. And then if I got a physics major out there, that's how you find the equations of motion of the electron whipping around the hydrogen nucleus. Okay, so the point, yeah.
Bobby, you mentioned though that like they programmed this wrong, the defense budget, their money, like they.
It happens all the time.
Yeah. So the problem is though they put that all in a language called COBOL that nobody under the age of 60 knows and it isn't taught anymore. So that's why none of this stuff's ever going to change. They've been looking for like 70-year-old programmers this whole year, since that's what our unemployment's built off to. So it's like an old language that nobody uses. So the government.
Hey, I can still do a little bit of Pascal, maybe.
Yeah.
Maybe.
Yeah. Maybe they'll.
Cobalt came for Cobalt's old.
Yeah, Cobalt's I think one of the I think it's like the second or third language ever invented. So
Okay, Cobalt and then Fortran, then Pascal.
Yeah.
And then C.
Yeah. So we're way long time ago. So that's why we have all these problems.
Yeah, these old things. Not to get off the subject here, I'll finish this problem, but my wife has a friend at work, her husband, who's a dentist. He plays in a Judas Priest cover band.
Nice.
And
you play the flute real quick? Is he the flute player, Judas Priest?
No, he's like he's either Tipton or Downing, you know, but he's a real square looking guy, you know. But anyways, he was telling me the things that are golden right now are these. You remember the old pedals from like the 80s, like a distortion pedal or like a delay pedal? He said that that technology, they stopped making stuff like that, and anything they try to make. So those things are priceless. If you haven't stumbled across any of those in a garage sale, grab them all. Okay, so with these conversion equations for x, y being converted into r and theta, we have r being the square root of x squared plus y squared, and the theta being the tan inverse of y over x, with a little, hey, you got to think about it. Okay. Now, I'm sure that Cobalt programmers and Fortran programmers and Pascal programmers came up with a way of distinguishing between these two things. Okay. I took Pascal, well, the first time I to drop it. The second time though, I could see like you would enter in a Y and then enter in an X. And then you would have it say, okay, if the Y is negative, we're down here, you know, and if the X is negative, we're over here.
Yeah.
You know, you have these like if-then statements.
You have to do all this in there.
It was very logical. There was something very satisfying about writing these programs that worked, you know. It's like,
I don't want to get too far off the subject, but real quick, in Fortran or Pascal, did you guys have object-oriented programming? Like, could you make functions that would deal with that, or was it just?
no, it was not object-oriented.
Oh,
If you
so
wanted
it's procedural.
if you wanted the square root, like somebody had to write a program. I mean, I've asked you guys this before, you know, how does your calculator do that? It does something, right? It gives you a number, hit 17, put square root. It's going to instantaneously write out some number, 4 point whatever, you know. Blah, 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 blah. Okay, well, long time ago, somebody like me wrote a program to figure that out. And now with this object-oriented programming, you just take the object and I guess you just throw it in and you don't have to reinvent the wheel.
I mean, you can use libraries to do that, but like the main idea is you don't have to do everything just in like in one page. You can break it up into lots of different chunks. So you're doing that. But yeah, for square roots, that's key. They already have a library on every single language that does square roots for you. So you don't need to do that.
So in this class, we are going to actually figure this out. Okay. We're going to learn what the calculator does. Okay. Now to go from R and theta to X and Y, notice that the sine of theta is equal to Y over R, and the cosine of theta is equal to X over R. So that means that X is going to be R cosine theta, and the Y is going to be R sine theta. Okay. Okay, now, if R ends up being a function of theta, what we've done is we have a parameterization of a curve. Okay, and so we're going to be looking into that stuff. Okay, so graphs. Graphs of polar functions in the X, Y grid. Okay, now because it's in the XY grid, this is going to have some kind of stuff going on, all right? So in the normal XY stuff, like in my Math 30 class, we've been just talking about equations of lines. Here's a vertical line, and here's a horizontal line, right? Okay. So in R theta stuff, maybe R equaling some fixed number, like for example, R equals 2. What would that look like? Well, the set of all points that are a distance 2 away from the origin, that's called a circle, right? So this is a circle, radius 2.
If R equaled 1, it would just also be a circle, right? Just smaller radius.
Of radius 1, right? Okay, so these in polar coordinates, the R equal 2 graphed in the XY grid gives us a circle. Now, if I graph this in the R theta grid, it would give me a flat line, okay? Okay, now this is the one that's weird. Theta equaling a fixed guy. So like, for example, theta equals pi over 4. So pi over 4, this is the pi over 4 part of it. Okay. Pi over 4. All right. Here's the x and the y. Okay, so all of these points, they all have some kind of a r, but their theta is pi over 4. This guy, r3, but its theta is the same thing. Okay, so we're thinking that this is a half line or a ray, and it's just going to keep going. Now, my question is this point on that line? I'm asking this obviously because there's something interesting happening here.
Yes. That's
So, okay, fucking eraser. Stop. So, there. So is this point on the line? Well, first of all, its angle is weird, right? So its angle theta would be 5 pi over 4. Okay. So if I gave you a point P and said -1 pi over 4, does this point satisfy the equation? Is the theta pi over 4? Yes. But see, what happens is this point gets passed to 1 and 5 pi over 4. Okay. So it's a question of, did you convert yet? Like, you know, for example, when I'm doing rational functions with you guys, like f of x equals, here, real basic example, x squared over x. I always assume our fraction is simplified, okay? Now, some of my colleagues, if you would say, okay, well, what does this graph look like? They would say it has a hole. And some of my colleagues would say, no, it doesn't have a hole. It's perfectly fine. Okay, well, maybe us at OCC aren't as smart as other people. So I go over across the freeway or go over there to UC Irvine and find all those real smart people and ask those guys, and you'll have the same thing. About half the people will say, yep, there's a hole, and the other people will say no. Okay, so it's kind of like to be determined if this is going to be on there or not. Okay. Now, again, we have all these issues because of these identifications that we're making with things. We're saying that, you know, there's infinitely many ways to represent the origin or do this. Okay, so if we were to graph a guy, so for example, if we were to graph R equal to, let's say, cosine theta, let's see what it would look like. Okay, so it's kind of always good to have a cosine curve hanging around. Okay, so the cosine is going to get separated up into 4 regions. Theta is going to go from 0 to pi over 2. Okay, so that means R is going to go from 1 to 0. Okay, so over here, try to draw the graph. So, and I don't need that. Okay, so theta is going from 0 to pi over 2. So here's 1, okay? So this is the point 1 comma theta equals 0, okay? And as this theta increases, you can see that the cosine is decreasing down to 0. So what's happening is it's going like this, okay? In the second region, theta is going to go from pi over 2 to pi. So the r would go from 0 to -1. That means the r is negative. So we have to pass off. So our new thetas are the theta going to go from 3 pi over 2 to 2 pi. And now the r goes from 0 to 1. Okay, so here is the 3 pi over 2 line. The r started at 0. Fuck me, this stupid thing. You just use your undo trick. Okay. So it's going to come back around and go back up. Okay. Now, just to make sure that it doesn't do anything new, let's go theta, going to go from pi to 3 pi over 2. The r is going to go from -1 to 0. So that means the r is negative. So we need to pass off to new plot points. So we add pi to all of these, and that's going to be 5 pi over 2, which is going to be from pi over 2. I mean, no. Do the second one first. Okay, so the new thetas are going to go from 0, because 2 pi is 0, to 5 pi over 2, which is going to be the pi over 2. So what's happening is we go up here the first time, the second time we're coming here, then we're traversing this a third time, and then we're coming back over here a fourth time. Okay, so we're going to have to remember this, because when we go to compute arc lengths and areas and stuff, we have to remember that for r equal cosine theta, it graphs it once from 0 to pi. Okay, now notice something, that this is not a function. It doesn't satisfy the vertical line test, right? But in terms of r and theta, it's a really nice function. You know, it's very specific. All right, well, turns out that if you were to graph r equaling the sine of theta, you're going to get a circle again that's going to be up here like this. And it's going to be going like so. Okay, so are both of these things actually circles? Let's see. If I started off with r equals cosine theta, multiply both sides by r, use the conversion equations, and so this is the equation of a circle. X squared minus x, we're going to complete the square, take half of this number and square it, okay? Take whatever you did to that side and do it over there. X minus 1/2 squared plus y squared equals 1/4. So what we've got here is a circle of radius 1/2 whose center is at the point 1/2, 0. All right. Okay, so if we go to a new example now, like let's say we tried this, r equals 1 plus the sine of theta. Okay, one might naively think to take this picture and just move it up 1 unit, but it's not going to work out that way. Okay, so again, let's have a sine curve laying around. Okay, so pi over 2 pi, 3 pi over 2, 2 pi. So the first region we'll go in is going to be the theta is going to go from 0 to pi over 2. So that means your r is going to go from 1 up to 2. All right, so over here on the side here, I'll start drawing a picture. So here's the x and the y. Okay, so the theta is going from 0 to pi over 2. So it's starting at 1. And there's a 2. So what's happening is it's going to go like this and eventually do this. Okay. Then number 2, when theta goes from pi over 2 back down to 0, the r is going to go from 2 to 1. And this is important, in the exact same way that it went up there, meaning that these sides of the sine function, they're the same, just inverted around. Okay, so then this guy's going to come back around and hit the negative 1 like that. Region number 3, pi over 2 to pi. Okay, region number 3, theta is going to go from pi to 3 pi over 2. Okay, so now the r is going to be subtracting stuff. Okay, so the r is going to go from 1 to 0. So that means it's going to go in here and do this. And then region number 4, it's going to go from 3 pi over 2 to 2 pi, and it's going to come back up like this. Okay. And as I told you guys, this is called a cardioid. Looks like a butt, right? Okay. And depending on what you're doing with the r equaling 1 plus or minus sine theta, r equals 1 plus or minus cosine theta, there's one for each of these guys. Okay, so the 1 plus sine theta is the butt down. And let's see, there's going to be a butts up one. So there'll be one like this. And then there'll be a sideways butt, like forcing that way. And then there'll be another butt going the other way, like this one. Okay. So you guys can, work all these out. Now, we are not going to really get carried away with this. The pre-calculus book just really gets involved. When we have r equaling a plus or minus b sine theta, or the r equaling a plus or minus b cosine theta, what happens is you start getting very odd shapes. Like you start getting things like, the cardioid, where it goes like this, and then it might loop around like that and go up like so. Okay. It might be that it dents it, so it comes out like this and then it just dented it and went back to the thing. Okay. All right. Now I'm not want to redo this since our goal here is calculus. So if you go through and graph these guys, like r equals the sine of 2 theta, what you end up with is a flower. Okay, so what happens here is you get it going like this. This guy comes down here, goes up here, comes around. Okay, so this is the graph of r is the sine of 2 theta with 4 leaves. R equals the cosine of 2 theta. It again is a flower that has 2 leaves, 4 leaves. Okay, but this one starts off different. So what this one does is when theta is 0, r is already 1. So it's starting up here. And it goes down, down. And that was too big of a pedal. So it comes here and it goes down here loops around here, comes back around here, picks up back around here, and goes back to there and back up to there. So the cosine pedals are on the axis, okay? Now, if we do sine of 4 theta, we're going to have 8 pedals. And this is a calculus class, not a polar coordinates class, but so we're going to have to fit 2 in each quadrant. So 1 there, 1 there, 1 there, there. And they're all symmetrically spaced out and so on. Okay. Now it turns out that when you do R equals the sine of 3 theta or the cosine of 3 theta, we get 3 pedals. So you guys can play around with, you know, with those if you want. Okay. We of course want to be doing some calculus with this stuff, but before we, you know, get all carried away like that, let's make sure everyone's all caught up. All right. So as far as homework problems to do, we all are maybe looking in different books, but I'm in 10.3. Do some. You know, don't just wait for the assignment tomorrow. You know, just get in there. Like, you need to be learning this stuff because I'm telling you, at some point in time, we are going to go back to school and you're no longer going to be able to have a little group chat going on the side computer. Like, anybody solved number 6 yet? You know, anybody find where number 7 is on the internet? So, but at some point in time, you know, you're the crew that has to know this stuff, you know, so do some of those guys. Okay. So what we'll be doing tomorrow is some calculus with this polar stuff.
Yay.
Yay. And we'll get some interesting results and equations and things. So let's turn this guy off. Stop.
I mean, the polar coordinates seems fun and interesting to do, but the calculus version where you can actually apply it to something excites me more than drawing flowers.
Yeah, they use polar coordinates to make. He has little stories in here, you know, with the Bezier curves and you know, that eventually what we're going to do is we're going to look at orbital mechanics. We're going to look at like the conic sections again.
Oh, okay.
And we're going to like try to distinguish between a really flat orbit, you know, like Halley's Comet, versus like Mercury's orbit that is like very circular. Okay. So there's a number that we call eccentricity. And when we write those conic sections in polar coordinates and put them in some kind of standard form, we can just read off that eccentricity.
Oh, okay.
So like, I'm just watching the Science Network today, and there's some long cigar-shaped object that's hurtling in towards the inner solar system that did not originate from our solar system. It's about they estimate the size of the Empire State Building. Okay.
Oh, you're talking about the comet that looks not a comet, the meteor that looks like a giant turd that's spinning in a weird way. Yeah.
And it's all, yeah, okay. Which, by the way, you learn in physics, you can't have stable 3-dimensional rolling. Like if you're stable this way and this way, you can't be stable in the other way.
Yeah,
So
it's,
anyway.
it's supposedly doing this, and they don't know why it's doing this rather than doing this, or like you said, doing the other thing like that.
Well, you can have stable this, but
Mhm.
then this stuff will not be stable. I remember doing this in mechanics. Okay, well, anyway, so what happens is if you see something like JPL guys, they see
Mhm.
something in the sky, a comet's coming. Okay, so they do some measurements, and it's a measurement of the potential energy. Okay, and then you do something with that function, like you take its derivative, and if it's positive, you know the orbit is something like a hyperbola. If it's 0, it's a parabola, and if it's negative, it's an ellipse. Okay, so if the orbit is hyperbolic or parabolic, then you calculate, here's the Earth, is it going to hit us?
Mm.
No. And we don't have to worry about it ever coming back because its orbit was not elliptical. But if that measurement from the potential energy function is a certain thing, it means the orbit is elliptical and it's got to come back. And so those are the ones that everybody's tracking. Okay. There's lots of them, and there's lots more that we haven't seen. Just like what did Billy Bob Thornton say in Armageddon? It, with all due respect, sir, it's a big goddamn sky. You know, like that.
The old guy.
Yeah.
I love that movie. That movie was a really big eye opener when it comes to how we're somewhat prepared, but it's still a movie. But like the way they emphasize, like you just said, it's a very big goddamn sky. You know, we only know this.
There
we
is
can
one
only
that
see
is
this
coming.
much of a square of an area when the
So
rest
there's one that's coming.
Yeah.
And everyone knows about it, and it's supposed to hit in about 40 years. And
Oh.
it's an extinction level event.
Uh-huh.
Okay. If it hits just perfect. Okay. So here's what NASA's big plan is. They're going to launch like an empty thing, and they're going to shoot it around some planet like Mars or something like that, and then park this thing. Let's say the Earth is.
They're gonna put a mass next to
So
it.
like
so
the Earth
it's
is where my elbow is. So the Earth is like right here.
Mm-hmm.
There. Okay. So the whole idea is park this thing next to it, and it'll have enough gravitational attraction between the two of them that'll just miss.
Yeah.
So seems like a little Wile E. Coyote to me, but that's the plan on how to do it. And
well, doesn't the object have to have a bigger mass than the object that it's trying to get next to, so that way the mass from the bigger object pulls the other one?
No, they pull together.
Oh,
Now
okay.
it might be like this, where one is a lot more mass, but all they need is just if this is the bad guy, all they need is just a little bit, and go like that.
Okay.
People are thinking Tunguska was a comet. Now everybody's reconsidering that theory, even though it seemed like all of the analysis was pretty spot on with that. Okay, any problems that you guys didn't succeed on, and you want me to do it? Anybody know the order?
I've been just looking at gamma videos, like for the gamma functions that you showed us in class.
Oh, okay. Yeah, make sure you do some arc length and some surface area stuff, because all that's just more integration for us.
Oh, okay.
Okay.
Professor, when you get the chance, can you check so that see if you received my exam?
Okay, let me look. Let's do that right.
I can send it again though.
Okay, hold on. Let me look. So let me.
And also, are you going to release the exam earlier tomorrow or the same time as the class starts?
It'll probably be a little bit before the class starts. I'll probably be doing the exam tomorrow. Okay, so it's not where I want to be. I want to be in my mail. Okay, so you sent it to me in an email, right?
On Canvas email, yeah, through Canvas.
And you did this today?
Oh no, on July 7th, on
Okay,
the exam day, at 8:33.
okay. So that was on a Tuesday?
Yes, last week.
Because it's not giving me days, it's giving me Wednesdays and stuff. Okay, here's Tuesday. I got something from, what was your last name again?
Diana Nejad, Charmin, Sharmin. Oh, bless you.
Nope. So it didn't come into my OCC email. And if I try to get into my Canvas email, I don't think I can stay in the Zoom meeting.
Hey, Professor.
Yeah.
So I had a question on the exam you graded. So you marked 2 of my questions wrong, but I understood why you marked one of them wrong, but the other one I didn't understand. I thought I got it right. So it was the 7th one, which
Okay. I'm gonna see. I can't get to this stuff when I'm in this.
Oh, on Canvas email, you mean, or?
Well, I can't get into. Like,
I will email you again the exam and a screenshot when I sent the exam to you, and you can go back later and check.
okay, well, I don't care when you send it. I mean, I'm trying to.
I just sent it to you right now
Okay.
on your regular email. Or your
Okay.
email.
So for you guys, I will.
Yeah.
I'll go do this stuff right now before I start doing anything else. All right. Check my email. I'm gonna look at all the blanks. Okay.
Yeah. Could you check my paper if it's possible?
Yeah. And what's your name?
Gopal. Last name is Nukula, NOOKULA.
Here, why don't you email me your question, Muir at OCC. That way I can just directly go back to you.
Okay, so the Canvas thing.
No, don't do it in Canvas. Just go Muir at occ.cccd.edu. Because apparently submitting it in Canvas doesn't automatically load. But now I want to go check this.
Yeah.
Okay, everybody.
Okay, thank you, Professor. Have a good night.
Thank you so much.
All right.
Yeah.
Stay classy, San Diego.